Hey guys, welcome on my channel and welcome to a new video. Today we want to take a look at the optimization of a crank gear. A crank gear is, in its simplest form, a mechanical aperture which consists of a crank arm which is attached to a rotating shaft. And this is used to transform circular motion into linear motion or into something different. A famous example is, for instance, the manually operated car windows. You know, where you have to rotate the shaft to open the window. And if you do this on a more abstract level, a crank gear consists of 4 points. 2 of them are fixed. They are called A and B. And the point P is rotating around A. This is our circular motion. And the point Q, which is attached to our crank arm here, is now moving into a circle or into part of a circle around the point B. So let's take a look at the simulation, how this looks in motion. Here you can see that the point P is moving in a circle around A with constant angular velocity. And since the point B is fixed, the point Q is moving in a way which is determined only by the length of our crank gear and our crank arm here. And the question is now, can we optimize the system to get our point Q moving the way we want it to move? And that's the aim of this video. I want to show you how to do this in Matlab. But before we start with the optimization, we have to do some geometry and take a look at the geometric constraints. Let's start with giving some objects some names. The distance between the point A and the point P is called L1. Between P and Q, L2, between B and Q, L3, and between A and B, L4. The parameters L1, 2, 3, and 4 will be our optimization parameter later on. But before we come to this, we have to exclude some singularities. Namely, we want to avoid that A is equal to P because there would be no movement. And with singular argument, we want to exclude that P is equal to Q. And we do this by introducing the additional constraints L1, L2 should be bigger than Lmin, and Lmin is bounded away from 0. So this is, from a geometric point of view, very clear. In addition, we introduce the following constraint: L4 should be bigger or equal than L1 plus Lmin. What's the idea behind this? Well, P is rotating around A. And we want to avoid that at any point, or at any time in this rotation, the point P should be equal to the point B. So therefore, we introduce this constraint here. Therefore, this clearly ensures if L4 is bigger than L1, then P can never be equal to B. And this, of course, is also very clear from a geometric point of view. Now things become a little bit more complicated. Assume the following situation. The point P is completely rotated to the left of A, and the point Q is lying on the line between A and B. So we have this situation here on the right. Then we can take a look at the length PQ plus QB. This is the whole line here, length of the whole line. And if this is less or equal than PA plus AB, there is no chance that the point P can freely rotate around the point A. This is physically impossible. And this is something we want to avoid, and therefore we impose the constraint that L2 plus L3 should be greater or equal than the point L1 plus L4 to ensure that the point P can rotate freely around the point A. A similar situation, but now the point P is rotated completely to the right of A, and again Q is now lying on the line between A and B if this is extended to the right. And with similar arguments, there would be no physically rotation of P around A possible if this condition here holds. I mean, just take a look at the distance between P and B, and if this is violated here, there cannot be a rotation around A. So therefore, we impose the condition that L2 minus L3, or the norm of it, should be greater or equal than L4 minus L1. However, this is something discontinuous here, and we don't want this here. So therefore, we just put a square on both sides and end up with that the square of L2 minus L3 should be bigger than the square of L4 minus L1. In this slide, I gathered the information which we obtained in the last 2 or 3 minutes. On the left side, you can see our crank gear, and on the right hand side, you can see the 1, 2, 3, 4, 5 constraints which we need to impose to ensure that the point P can freely move around the point A. Let's take again a look at the simulation, but now with additional information. I added the movement of the point P and of the point Q and some angulars. The angle at the point A is called T, and the angle at the point B is called omega of T. And you can see the point P is making a whole circle, while the point Q is moving parts of a circle. We want to optimize the movement of the point Q, but the movement of the point Q is fully determined by the length of BQ and the angle omega T. So it is in fact sufficient to control the angle omega T. And this is what we want to do now. We want to determine the length of the parts of the crank gear so that our angle omega T is moving just the right way we want it to move. So here again, you can see it in the non-moving version. We want to optimize the function omega of T. And it's clear that the function omega is somehow fully determined by the angle T and the parameters L2, L3, L4. And it's now our job to determine a algebraic formulation for our omega T so that we can actually do some optimization. So let's start with some geometry. We start by giving some angles some name. The angle between A, B and P is called omega 1. The angle between P, B and Q is called omega 2. And it is clear that if we are able to derive formulations for omega 1 and omega 2, then our function omega is just pi minus omega 1 minus omega 2. And for this construction, we'll need the length between P and B, and this is denoted with U of T. So let's start with the following formulation. The angle omega 1, well, it can easily be derived. This is just the tangents of this angular. It's just this length divided by this length, and this length is just L1 times sinus of T, and this length here is just L4 minus L1 times the cosinus of T. This is very easily be determined. To get a formulation for omega 2, we start by using the Pythagorean theorem for U of T. So U square of T, which is just this length, is by Pythagorean theorem is just, well, this length here, but this length here we just computed as L4 minus L1 times cosinus T to the power of 2, and this length here is just L1 of sinus to the power of 2. And now do some multiplication, and you will see that we end up with the expression that U square of T is just L4 to the power of 2 plus L1 to the power of 2 minus 2 times L1 times L4 times cosinus T. And this now will help us to determine a formulation for omega 2. It's the same argumentation as we use for our for the calculation of U of T. It's just the same trick. Or use the general cosinus theorem in an arbitrary triangle if you want to. This will also give you this result that L2 to the power of 2 can be expressed or is equal to U squared plus L3 squared minus 2 times UT L3 cosinus omega 2. And this here you see the term we are aiming for. You can see omega 2. And as already mentioned, omega can now be expressed as pi minus omega 1 minus omega 2. So here you can see it on one slide. You can see the 4 equations we just have derived. And the job is now to reformulate this equation so that we end up with algebraic equations for omega 1 and omega 2. But this is not so hard. You can see it here. You have to take a little bit care to check that this term here is actually non-negative, but by our constraints we just impose, this can be guaranteed. Same holds for the arctangents and the arccosinus. So finally, this here is the expression for our calculation of omega. Now we have everything at hand to actually formulate some optimization problem. And we already mentioned that we want to steer the angular omega as close as possible to a target function which I called v, or in fact, if you're thinking about inverse problems, optimization problems, this is actually our desired state. We want our system to be steered to the desired state as close as possible. And just a quick notation to underline the dependency of omega from our vector L, and L consists of the length of our crank gear. We just added as an additional argument. This is just for readability. Let's take a look at the optimization problem. What does it mean to steer a function as close as possible to another function? You have to take a norm at somehow, and the fairest or the most intuitive is to use the L infinity norm or the maximums norm. So in fact, we want to minimize the maximum difference between v and omega, in addition, of course, to our constraints, to our geometric constraints. And this here now is the classical min-max problem, and this is not so easy to tackle, especially since omega is a highly nonlinear term. I mean, it consists of some arctangents and some inverse cosinus and square root and stuff like that. But our first step is to tackle this continuity here, because we are minimizing the maximum of every point between 0 and 2 pi, and these are infinitely many, and this is of course hard to tackle. But what we want to do is we want to somehow sample the interval 0 to from 0 to 2 pi to make it more accessible for our numerical solvers. Speaking of numerical solvers, the aim of this video is not to talk about existence or uniqueness or conversion speed or stuff like that. This video is more about modeling optimization problems and solving them without taking care about existence and stuff like that. So just keep this in mind. So back to our discretization or to our sampling of this interval here. For sampling, we need some sample points, and we call them Ti, and they are of course between 0 and 2 pi in an increasing order. And instead of maximizing the whole interval, we're just maximizing at these sample points. Of course, we are doing a discretization error here, and again, this video is not about existence uniqueness and how big is the error we're making here. It's just, I want to show you this technique of getting stuff done. You want to solve it, you want to pass it to your numerical solver, and your numerical solver cannot deal with infinitely many points, so you have to find a way around it. And one way to do is by introducing the sample points here. So this is now it's still a min-max problem, but we have taken care about this continuity here. Of course, if we choose k to be too small, the error might be too big, and this is of course to be determined, and of course must be analyzed in some sort of way. But let's talk about how to get rid of this min-max problem here. In the following slides, I want to show you a trick which is commonly used to get rid of some maximum terms. And to introduce this trick, we consider the following optimization problem. Again, it's a min-max problem. We're minimizing over some set, the variable is called x, and we're maximizing over some sample points here. We now start with a reformulation. We introduce a variable delta, which has a dependency of x, and it's just the maximum of our sample points. And with this reformulation, we can just rewrite the optimization problem as minimizing over delta of x. This is not clear. And the trick is now we can decouple delta x from x by introducing this delta not as a function, but as an additional auxiliary variable. What do I mean with this? Well, the optimization problem you can see here can be reformulated as the following. And you can see the difference here, that we are still minimizing over delta, but delta is now decoupled from x. It is an additional variable which we are minimizing. And the trick comes here. We introduce the following additional constraints. Minus delta must be less or equal than f, ti less or equal than delta, and this must hold true for all our sample points. So in fact, if this inequality here holds, then the maximum of f of x of ty must be less or equal than delta. And since we are minimizing this, we are maximizing this term here. So this is just a small trick, but a very useful trick. And people sometimes call this the epigraph formulation, because we're actually imposing constraints on the epigraph of our function f here. And well, you can just do quick calculation and you will see that these optimization problems are in fact equal. And this is a nice trick to get rid of min-max problem and to actually make it solvable for numerical programs or solvers. Let's do this for our optimization problem here. Again, our sample points are t1 to 2k, and we are introducing delta as an auxiliary variable, but this maximum of v minus omega is now moved to the constraints here. And well, this is our final optimization problem here. We now let's recall it let's record what have we done. We have introduced the sample points to get rid of this continuity, and by this small trick we have get rid of this maximum in our objective function and move this to the constraints. And well, these are now non-linear inequality constraints, but this is something we can tackle. There exist solvers for this. For instance, the famous or infamous, whatever you like, fmincon of Matlab. Fmincon cannot directly tackle such min-max problems, but it can directly tackle such nonlinear inequalities. And that's what we're gonna do in the next steps. We want to reformulate, or we want to write this into a Matlab script which actually solves the optimization problem. We start by setting up our function omega, and for our function omega we needed the explicit formulations of omega 1, of u, and omega 2, and we'll just plug it here. Omega 1 was the arcus tangens, u was some square root, and omega 2 was the a cosinus of something. And omega was then pi minus omega 1 minus omega 2. Just write it down in this very simple form. More interesting is we need to set up our objective function. Remember, we just want to minimize delta. So our function x consists not only of our length of our crank gear, but also of this auxiliary variable d. So we want to minimize d. I choose it to be in the first position of our solution of our optimization variable, and therefore the optimization or the objective function, I call it fmin, is just x1, or the first component of x. Nothing spectacular here. More interesting is the setup of the linear inequalities. we have 4 linear inequalities. You can see that here. And we have to reformulate them as a matrix inequality. And so AX must be less or equal than B. And well, this is straightforward. I've written this in this form, and you need to reformulate this into this form here. And just reformulate this as a matrix vector inequality. Really nothing spectacular going on here. More interesting is now the setup of the nonlinear inequalities. We have some nonlinear inequalities. Let's start with the nonlinear inequality, which was L2 minus L3 squared must be less or equal than L4 minus L1 squared. And we have to reformulate this as a something must be less or equal than 0. So just bring this to the other side. And at the first position of our nonlinear inequalities is now this expression here. And now we are taking a look at the sample points or the nonlinear inequality constraints arising from the sample points. We have to split them into 2 parts because we have minus delta was less or equal, something was less or equal than delta. And you can see this here. So we just rewritten this into 2 nonlinear inequalities. And that's all you need to set up your nonlinear inequalities. This is actually very easy. You just call the function v, which is to be determined. This is our desired state. The function omega, I've just showed you how to define this, and that's all you have to do. We are left with setting up the solver, and the solver is well, quite easy. We generate our linear inequality constraints, and we have to impose some starting point, since I want to use the interior point function of fmincon, and therefore we have to impose a starting point, and the starting vector or starting point needs to satisfy our constraints. So I played around a little bit with the numbers, and I ended up that this value of L1, L2, L3, L4 satisfies our constraints. And therefore it is a valid starting point for our interior point algorithm, and I can just pass it here to our fmincon function. And that's all you have to do. That's basically all you have to do in Matlab is just writing this 10 or 20 lines of code, and you can solve your optimization problem. One last thing we have to do, we have to define our desired state. And I choose the desired state to be this function here. You can see the Matlab code on the right hand side. This just consists of a linear increasing part followed by a linear decreasing part. And now we want to check how good is our solver and how good can this function v of t be approximated, or how good can our system be steered to fit this function v of t. We start by taking 10 sample points, and on the top you can see our optimized crank gear, and below you can see the function omega t plotted against the desired state. And you can see that we are actually that we are getting close to the desired state, but not so good. And so maybe we can increase the accuracy if we increase the number of sample points. So what happens if we increase the number of sample points? You can see the result here. Now we are computing with 50 sample points. And first note that we are now getting closer with omega to our desired state. This is a good observation. But on the other side, take a look at the values of our x and y axis of our simulated crank gear. You can see the system looks not so nice. It looks a bit weird, but we have huge numbers going on there. And this is not so desired. maybe this thing go away if we increase the number of sample points. Let's increase it to 500 and see what's happening. Well, we see two things. First of all, our desired state is now quite good reached by our omega function, but to which price? Our crank gear system is now looking really weird. It looks really lengthy and you can actually see nothing. And there's a reason for this. Namely, the length L2 and L3 are going to infinity. This is something we do not want. This is a valid solution of our optimization problem, but in the modeling processes, we missed that the length of our crank gear could go to infinity. We have bounded it from below, and but not from above. If you put the solutions side by side for the different number of sample points, you can see, in fact, that we are getting an increase in accuracy, meaning that our function omega gets closer to our desired state v, but our system looks worse. So we are losing physical credibility somehow. This is not something you will pass to your engineering department and they will say, yeah, cool thing, let's build it. In fact, they will say, well, how should we build this? This is not possible. So you have to think about something else. And of course, if we have bounded it from below, we should bound it from above. So let's extend this model. One way to tackle the issue that our crank gear is going to infinity is, well, by adding additional constraints. So we want our Li, so L1, L2, L3, L4, to be less or equal than a certain value L. But I do not want L to be fixed. So I do not want to say, well, it should not be bigger than 20, 30 or whatever. I want to make it a little bit more sophisticated. You can see the upper bounds here, but as you guys already, I'm pretty sure you have noticed that this L is also popping up here in the objective function. What does this mean? Well, we're still minimizing delta, and the system also wants to steer omega as close as possible to our desired state v, but not for any price. There is a price. If you want to steer omega even closer to v, maybe your upper bound will explode, and this will cost you something. And to balance this cost, right, I introduced this factor L in the objective function to kind of, well, to balance these two objective functions. Of course, this factor C1 is to be determined, and in the simulations I will show you in a moment, I set it to be 0.01. And this is now an extension of our model, and I'm pretty sure you can think of many other cool things you can build into this model. Well, feel free. But I want to close this video by showing you the comparison of this extended model with the, let's call it, standard model. On the right hand side you can see the extended model, and on the left hand side you can see the standard model. Both are calculated with 500 sample points, and the factor C1 is set to be 0.01, I already mentioned this. And you can see that the results do not differ that much, except that the physics looks way more reliable in the extended model, right? Because there we are bounding the crank gear and forcing them to be more, well, to be more realistic in a certain way. So thank you all for joining in and staying with me. I hope you enjoyed this small video about optimization, modeling of a crank gear. And well, I hope to see you soon. Take care and, well, see you around.